Hello and welcome to this presentation related to energy methods as applied to combined angular and linear motion problems. In part 1 of the presentation we considered energy methods applied to purely angular motion problems, but in this part 2 we're now going to consider, for example, a disc or a shaft that's rotating with angular velocity about some axis, whilst also having a linear velocity v. So we'll derive equations for the kinetic energy of motion in terms of both linear and angular energies. This presentation builds on the previous part 1 presentation related to angular motion, but also on the previous presentation related to energy methods applied to linear motion problems. Here's a brief overview of the presentation related to both angular and linear energies. Approximate timings of the various sections below are stated in the square brackets. The presentation commences with a brief introduction to some new theory and a recap of the equations from the previous presentation, 2 minutes into the presentation. Question 5, which relates to a flywheel and a hanger, commences 6 minutes into the presentation. The flywheel has angular motion, the hanger has linear motion. Question 6 considers a wheel and axle rolling down an inclined plane. That starts 29 minutes into the presentation. The wheel and axle has both angular and linear kinetic energies. And finally, question 7 relates to a truck being hauled up an incline by a winding drum or a winch, commences 37 minutes into the presentation. In this case, the truck has linear motion as it's hauled up the incline. The winding drum has angular motion. So let's consider the total kinetic energy of a rotating wheel or disc or shaft. So if a wheel rolls, then the total kinetic energy is a combination of two parts. Part A is the kinetic energy of translation of the center of the mass. That's a linear kinetic energy term, half mv squared, where v is the linear velocity. And also part B, the kinetic energy of rotation about the center of mass. So the kinetic energy of rotation is due to angular velocity omega, and the formula for angular kinetic energy is a half I omega squared, which we reviewed in the part 1 presentation. In practice, the center of mass usually coincides with the axis of rotation as in a rolling wheel. If v is the wheel linear velocity, I is the moment of inertia about the axis of rotation, then the total kinetic energy of the wheel, Ke, is a half mv squared added to a half I omega squared. Again, remember from our previous presentation, moment of inertia I is equal to mk squared. That's mass multiplied by the radius of gyration squared. All that's happened on the next line is it replaced the I with the mk squared here. If the rotation occurs without slip, and noting the angular velocity omega is equal to v divided by r, where r is the radius of the wheel, then we can now replace the omega squared term here with v squared upon r squared. Just another variation of the formula for kinetic energy. Again, within this work we refer to the equations of both linear and angular motion for constant acceleration. We reviewed these in our previous part 1 presentation and derived them in the angular motion presentation. Here are some energy forms to be aware of in both the linear and angular senses. So work done in the linear sense is the force multiplied displacement, or the distance travelled. Kinetic energy is a half mv squared. And potential energy, often written as mgh, is actually expressed as mgs here, where h is height fallen through and s is distance travelled. Sometimes they're one and the same thing. Work done in the angular sense is the applied torque multiplied by the angle turned through, theta. Theta's in radians, of course. The kinetic energy is a half I omega squared. And be aware of the other quantities. M is mass, W is the work done, T is the torque, I is mk squared. In some questions we'll be determining the power requirements. P is the torque multiplied by the angular velocity in radians per second. Some of the questions will ask us to calculate the maximum power, so that will be torque multiplied by the maximum angular velocity. Sometimes the questions will ask for average power, so that will be torque multiplied by the average velocity in the system. Further relationships to be aware of: distance, S is r multiplied by theta, again theta in radians. R, the radius, is always in meters in dynamics. And linear velocity v is the omega r, the angular velocity multiplied by the radius, again in meters. So within this presentation, we're now going to consider various questions extracted from our worksheets, and we'll outline the solutions on the whiteboard. In all the questions, we apply energy methods that involves an energy balance to solve for all the unknowns. So question 5. A flywheel having a mass of 25 kilograms. The flywheel is shown here in the sketch, front view, here on the side view. And that has a mass capital M, 25 kilograms. It's mounted on a shaft of 75 millimeters diameter. Here's the shaft, shown across here. It's mounted in 2 bearings, and diameter D is 0.075 meters. Remember, we always use meters when undertaking dynamics calculations. The shaft is located in horizontal bearings, shown here. Around the shaft is wrapped a light cord, to which is attached a hanging load having a mass of 2 kilograms. So here's the hanger, having the mass lowercase m here of 2 kilograms. Notice in the question it states a light cord is wrapped around the shaft. This is a cord here wrapped around the shaft. And the light cord is basically informing us to ignore the mass of the cord. It has negligible impact on the calculations. In practice, the cord is probably a piece of string. So if the load is allowed to fall from rest, as it unwinds from the shaft, it will begin to accelerate the flywheel. And in unwinding, the load is seen to fall 120 centimeters in 24 seconds. We're asked to calculate, by using an energy method, energy balance, the radius of gyration of the flywheel, usually given the symbol K. The effect of bearing friction can be neglected, so bearing friction is considered negligible in our calculations. So there's the question outlined, and for reference, here's an illustration of an actual flywheel used in an experiment. This is a much smaller flywheel than that of question 5, but it illustrates the various parts considered in the question. Here's the flywheel. Here's the hanger on which we locate the masses. And here's the light cord, or actually a piece of string in this case. It locates the hanger to the flywheel shaft here. And as we can see, the string is wrapped around the flywheel shaft. The end of the string is located around a small peg on the flywheel shaft that, once the string is fully unwound from the shaft, allows the hanger to fall freely from the shaft. So let's consider the experiment and applying an energy balance. We will consider position 1, where the flywheel is stationary, flywheel is at rest, and the hanger mass is released, hanger mass shown here, and starts unwinding from the shaft. This applies a driving torque, labelled T in the diagram, that begins to accelerate the shaft and flywheel as the hanger falls vertically down, through height labelled as H here. Just note for reference that H and S are interchangeable symbols within energy work. And note also that the mass is height H above the datum that we use for calculating potential energy. Considering position 2 now, here the hanger mass is totally unwound from the shaft. So the string here is at the extent of its length, and the hanger mass is about to fall to the floor. As a string of the hanger mass totally unwinds from the shaft, this causes a loss of the driving torque. However, at this point the flywheel is in motion, has an angular velocity omega, and at the point of release the hanger mass has a maximum vertically downward linear velocity labelled V here. So that's how we will apply energy balance to this experiment, considering the initial energies and any work in at position 1 and the final energies and any work out at position 2. So here's the solution for question 5. Extracting information from the question, we know the flywheel mass, that's capital M, was 25 kilograms. We know the shaft diameter, uppercase D, was 75 millimeters, and I said we always convert into meters when solving such dynamics problems, so that's 0.075 meters. The radius of the shaft, of course, is simply half the diameter, so that's 0.0375 meters. The hanger load, that's a mass on the hanger, lowercase m, was 2 kilograms. And the distance or the height fallen by the load, I've used symbol S here. S and H are often interchangeable symbols in energy work. And that's 120 centimeters in the question. And again, convert that to meters, that's 1.2 meters. The time taken for the hanger mass or the load to fall through height S T is 24 seconds. And we're told to assume that bearing friction was negligible. So here's the information extracted from the question. Question 5, solution continued. The left-hand diagram here, we have our hanger mass at position 1. When it's allowed to fall freely, unwinding itself from the shaft and applying a torque to the shaft and to the flywheel. At position 2, the hanger mass has now fallen through distance h, or sometimes termed s, and has now unwound itself totally from the shaft and is no longer driving the shaft and the flywheel. Notice that's the datum for the potential energy, this lowest point in our system. On the right hand side we've got an angular velocity omega time diagram, times in seconds here, and again it's showing the two positions. Position 1 here, as the hanger mass moves from position 1 to position 2, the flywheel begins to increase its angular velocity, producing this linear line. And remember, the slope or the gradient of a velocity time diagram is acceleration, labelled angular acceleration in this particular case. So at position 2, we'll have a maximum angular velocity of the shaft and flywheel, and of course we'll have a maximum linear velocity of the mass. If I was to draw the linear velocity time diagram, it would look exactly the same, just different numerical values on the vertical axis. So question 5, solution continued here. So now let's think of applying the principle of conservation of energy. For our previous work, that's basically the initial energy in the system plus any work into the system is equal to the final energy of the system plus any work out of the system. Now thinking of the energies in this particular case, with respect to our datum shown here, we do have initial potential energy of the mass. Relative to the datum, the mass on the hanger is some height away from the datum, so by definition it has potential energy. So on the left hand side of the equation we have potential energy, that's the mgh term. But at position 1 we have no linear kinetic energy of the mass because it is stationary, And we have no angular kinetic energy of the shaft and the flywheel because they're also stationary. There is no work into the system between position 1 and position 2. In other words, there's no external force pushing the mass downwards or no torque trying to accelerate the shaft. So there is no work into the system on the left-hand side of the energy balance here. All we have is the initial potential energy of the mass from the datum. If we consider the position 2, which is actually on the datum here, when the mass has fallen through height h or distance s, whichever term you want to use, now we have no potential energy because the mass would now be on the datum, so by definition no potential energy. But because the mass has been accelerating as it falls vertically downwards, and it has been driving the shaft in the flywheel as it unwinds from the shaft, we will have kinetic energy of angular motion, the half I omega maximum squared, and we'll also have the kinetic energy of the mass on the hanger, kinetic energy of the load, half mv max squared. Is there any work out of the system? Where there's no frictional resistances mentioned in the question, we can basically ignore frictional resistance, so there is no work out of the system. So all we have on the right hand side of the energy balance is kinetic energy of the flywheel because it's got some angular velocity, and we have the linear kinetic energy of the load, that's the mass on the hanger, because it's moving down vertically at some velocity at position 2. So that's my energy balance. So let's consider the information we know and do not know. We know the mass of the load on the hanger, so we've got the little m. We always know gravitational acceleration, 9.81 meters per second squared, and we have the height that the mass falls through. That's given in the question. But unknowns here include the I value, the moment of inertia, the maximum angular velocity shown here, and the maximum linear velocity shown here. Those are our unknowns. Now we know that the moment of inertia I is equal to mk squared. The capital M here is the mass of the flywheel, and we know the mass of the flywheel, that's given in the question, so we have that. And of course we're trying to find the radius of gyration, that's what the question wants us to find, so the k is the final answer we're trying to achieve here. So the two velocities we are trying to find, the maximum angular velocity and the maximum linear velocity. Now referring to linear motion equations, in the questions, we're given the vertical distance travelled, which is the s in this equation. We know the initial velocity u, because that's going to be 0. And we're also given a time in the question, so we have t. So rearranging this equation here, I can find the final linear velocity, v. So I can find that term here. And we do have a relationship we derived previously between linear velocity v and angular velocity omega. It's v is equal to omega r. So again, rearranging this equation for omega, we'll be able to find the omega max. So we need to transpose the energy balance to make I the subject of the equation. We can then solve for I. So the only value left to find will be the radius duration k. So quite a complicated thought process here to generate the energy balance and then decide what parameters we need to determine before we can solve the equation to find the radius of gyration. So question 5, solution continued. So here's our first calculation. We're calculating the maximum linear velocity of the 2 kilogram mass, or the load on the hanger here, after it's travelled through the distance of 1.2 meters. I'm using the symbol s here because it's s in the linear motion equation. Just for reference, notice in the question we are not given the acceleration of the mass, that's an unknown, but we are given the displacement, which is the distance s, and we are given the time taken. So that's why we deduced to use this equation from our linear motion equations. So rearranging to find the maximum linear velocity, that would be the velocity at position 2 on a velocity time diagram. The equation rearranges to 2 multiplied by s divided by t minus u. So inserting the values, that's 2 multiplied by s, which is 1.2 meters, that's the displacement or the distance between position 1 and position 2, divided by the time taken, that was 24 seconds, minus the initial velocity, and of course don't forget the initial velocity is going to be 0 because the mass and the shaft in flywheel commence from rest. So that's minus 0 in this case. That evaluates to a maximum linear velocity of 0.1 meters per second. From our relationship between linear and angular velocity, we can rearrange the v is equal to omega r so that the maximum omega, maximum angular velocity at position 2, this would be, that becomes the maximum linear velocity divided by the radius of the shaft. So that's 0.1 meters per second from above divided by the radius of the shaft, 0.0375 meters. So 2 2/3 radians per second is the maximum angular velocity of the shaft in flywheel at position 2. Question 5, solution continued. So returning to our energy balance, on the left hand side at position 1 we have our mgh, potential energy of the mass on the hanger. On the right hand side we have our kinetic energy terms for the flywheel and for the hanger mass. Notice from our previous work that moment of inertia I is equal to mk squared, so I'm just replacing the I in our energy balance with the mk squared because we're trying to find the radius of gyration. So in other words, replacing I here with the mk squared here. So I'm using here what I term my numerical approach. I'm just going to now insert the numerical values into this line of the equation. So on the left hand side the mass on the hanger is 2 kilograms, g is 9.81 meters per second squared, and the height or the distance through which the mass has fallen is 1.2 meters. On the right hand side we have a half multiplied by the mass of the flywheel, that's 25 kilograms. We're trying to find k, that's the unknown, and the omega from the previous slide was 2 2/3 radians per second. Of course we're squaring that value, and we add to that half multiplied by the mass of the hanger, 2 kilograms, multiplied by the maximum linear velocity of the mass on a hanger, which was 0.1 meters per second. Of course that's squared again. Evaluating, we find the radius duration k is equal to 0.5145 meters or 514.5 millimeters. And this is question 5, solution continued. This is purely for reference. This is what I sometimes term the algebraic approach to the solution. At this level of study, I encourage students to use algebraic manipulation as best they can to rearrange the equation for the unknown. In this case, the unknown is the k. So that's what I've done on this slide. I've tried to rearrange the equation algebraically to form this line here before I put my numerical values in. So to rearrange this equation here to find k squared, I've simply multiplied by 2 on the next line. That's why the 2 occurs on the left hand side, but the half disappears on the right hand side of the equation. And next I subtracted the mv max squared term from both sides of the equation. And finally I divided by the m and the omega max squared term here. Inserting the numerical values from this line here, of course we determine the same radius duration as we did in the previous solution. Just showing you slight algebraic manipulation of the equation before we inserted numerical values, that's all. This is question 5 continued. There's a couple of slides here for reference. Within our analysis on the previous slide, we used the principle of conservation of energy to show that the initial potential energy equated to the final angular kinetic energy added to the final linear kinetic energy. However, sometimes questions are expressed using different terms. For example, mgh, our potential energy, could have been written as the weight of the object, that's the mass times gravity, multiplied by the height fallen through. However, this could have been written as the weight is terms the force, and the height fallen through would be s, the distance travelled. So in other words, our mgh could actually be written as work into the system. So our principle of conservation of energy could have been written as linear work into the system, F multiplied by S, is equal to the two kinetic energies. Question 5 solution continued. Again, this slide is for reference. Another way the principle of conservation of energy could be applied was to consider the initial angular work in. Now, from our previous work, we know that angular work done is calculated by the applied torque multiplied by the angle turned through, where the applied torque T is in Newton meters and the angle turned through, theta, is in radians. From our previous definitions, we know that torque is actually, in this case, the force, F, that would be the weight force, mg, multiplied by the shaft radius, r. So that's half the shaft diameter. Here's another illustration. The force in the cable or the string, which is essentially the weight force on the hanger, F, multiplied by the radius of the shaft, r, calculates the torque applied, T. Now, to calculate the angle turned through, symbol theta, in radians, theta would equal to the height that the mass falls through, or that the force is applied, h, divided by 2 pi r, and don't forget 2 pi r is actually circumference, so dividing the linear height fallen through h by 2 pi r will calculate the number of revolutions turned by the shaft, and if we then multiply the number of revolutions by 2 pi, as in one revolution there are 2 pi radians, we can see that the 2 pi in the denominator cancels with the 2 pi in the numerator. So theta is actually h divided by r. So now if we replace the force in this equation by mg, multiply the force by the radius of the shaft r, and then multiplied by the angle turned through, theta, which is shown to equal h upon r. Again, we notice cancelling here of r in the denominator with the r in the numerator. So we can show that t theta, the angular work done, is equal to mgh, the potential energy. So an alternative form of the principle of conservation of energy could be angular work into the system t theta is equal to the two kinetic energies on the right hand side. So question 5, summary of the previous slides. In the solution of question 5, the principle of conservation of energy we generated had the initial potential energy on the left hand side of the equation, the mgh term, and that was equal to the angular kinetic energy of the flywheel, shown here, added to the linear kinetic energy of the load or the mass, shown here. However, the information in the question could have been given in a different form so that our principle of conservation of energy balance could have had linear work into the system on the left hand side of the equation, the force multiplied by the distance travelled, the height dropped in this case, again equal to the kinetic energies, or the energy balance could have had angular work into the system on the left hand side, the t theta, the constant torque multiplied by the angle turned through in radians, and again equaling to the kinetic energies on the right hand side. So our energy balance is dependent on the information given in the question, and this information can be presented in various forms, as tried to be illustrated here in this summary. Here's question 6. A wheel and axle has a mass of 4 kilograms and a radius of duration of 50 millimeters. Wheel's axle is 12 millimeters in diameter, and the wheel rolls freely down an inclined plane, shown in the sketch below. We're asked to determine what height the wheel moves through if it starts from rest at the top of the incline and has a final speed of 0.15 meters per second at the bottom of the incline. We're told to ignore any friction considerations. The answer for height h is shown in the bracket here. So the wheel and axle commence at the top of the incline, position 1, where it's stationary, and released and allowed to roll freely down the incline to the bottom, position 2, where it has not only a linear velocity but also an angular velocity. And of course these will be the maximum linear and angular velocities in this system. Notice the datum is taken at the bottom of the incline. We always take the datum at the lowest point in our system when evaluating the potential energy. That's just for numerical convenience. For interest, here's the radius of gyration experiment. Here's the inclined plane, showing position 1 of the inclined plane, just top of the inclined plane here, and showing position 2 of the inclined plane, the bottom of the inclined plane here. And here's the wheel and axle that initially starts at the top of the inclined plane and then rolls freely to the bottom of the inclined plane. This photograph shows the wheel and axle at the bottom of the inclined plane here. Diagrammatically, this is the scenario we're considering. From position 1, top of the inclined plane, the wheel and axle falls through vertical height h to the bottom of the inclined plane. Distance s here is the length of the inclined plane. Question 6, solution here. To extract the information from the question, the mass of the wheel and axle is 4 kilograms. The wheel's radius duration, k, stated in the question is 50 millimeters. As always, we convert that straight away into meters, so 0.05 meters. The wheel's axle diameter is 12 millimeters. Again, converting diameter into meters, 0.012 meters. Again, referring to the photograph, here's the wheel, here's the axle, and here's the axle diameter d. To calculate the axle's radius, of course, that's just the diameter divided by 2, so 0.006 meters. We can calculate the moment of inertia I in this case because we have the mass from above, it's 4 kilograms. We have the radius duration, 0.05 meters, so 0.05 squared here. So we can determine the moment of inertia for this wheel and axle, and it's 0.01 kilogram meters squared. Question 6, solution continued. Let's again consider our principle of conservation of energy and our energy balance, where we consider our initial energy in any work into the system is equal to our final energy in any work out of the system. So in this particular case, at position 1, the wheel and axle is at the top of the incline and it's stationary. So there, by definition, there will be no kinetic energies of linear or angular motion. But because our datum is placed at the bottom of the incline, we will have potential energy. So on the left-hand side, we have the mgh term. We're informed in the question that the wheel and axle rolls freely down the incline, so therefore there's no external forces or torques applied to the wheel and axle, so therefore there's no work into the system in this case. Considering our energies at the bottom of the incline, position 2, we know the wheel is rolling, so it will have by definition an angular velocity, and it will also have a translational velocity, a linear velocity as well. Those will be the maximum velocities in the system. So we'll have kinetic energy of linear motion and kinetic energy of angular motion. The question states to ignore any frictional losses, so we'll ignore any work out of the system. In this particular instance, we're trying to find height h here. So what do we know? We know the mass of the wheel and axle, we know the gravitational acceleration. So left-hand side is just h unknown. On the right-hand side, again, we've got the mass of the wheel and axle. We've got the maximum linear velocity, because that's given in the question at the bottom of the incline, is 0.15 meters per second. We've calculated the moment of inertia for the wheel and axle, and we can find the maximum angular velocity By using this equation here, the relationship between linear and angular velocity, we have the linear velocity v at the bottom of the incline, so we can rearrange to find the angular velocity omega at the bottom of the incline. So implicitly we have the maximum angular velocity as well. So we have everything we need to calculate the unknown height h. Question 6, solution continued. We know at position 1 at the top of the incline, the wheel and axle is stationary, so the initial velocity is 0 because it starts from rest. States here in the question. And at the bottom of the incline, the final speed is 0.15 meters per second. So the maximum linear velocity is 0.15 meters per second, bottom of the incline. From our relationship of v is equal to omega r, we derived in a previous presentation, we can rearrange to find the maximum angular velocity omega max at the bottom of the incline. And that's the maximum linear velocity divided by the radius of the axle. So that's 0.15 meters per second divided by 0.006 meters. That's the radius of the wheel's axle. So 25 radians per second is the maximum angular velocity at the bottom of the incline, position 2 here. Question 6, solution continued. So here's our principle of conservation of energy. On the left-hand side of the equation, we've got the potential energy at position 1 here. So that's the mass of the wheel and axle, 4 kilograms, multiplied by the gravitational acceleration multiplied by the height, which of course we're trying to find, h. And that's equal to, on the right-hand side, to linear kinetic energy added to the angular kinetic energy of the wheel and axle. So inserting the values of the half multiplied by the mass of the wheel and axle is 4 kilograms, multiplied by the maximum velocity occurs at the bottom of the incline, so that's 0.15 squared, and we add to that half multiplied by the mode of inertia, which is 0.01 kilogram meter squared, multiplied by the maximum angular velocity at the bottom of the incline, that was 25 radians per second, and again that's squared. Evaluating height h of the incline, shown here, is 80.8 millimeters. Question 7. A 500 kilogram truck is attached to a winding drum and is accelerated up a 5-degree slope of 30 meters length from rest to a speed of 2.4 meters per second. A 250 kilogram winding drum used has a diameter of 1.2 meters and a radius of gyration of 470 millimeters. The mass of the winding rope and inertia of the truck wheels can be ignored. We've got to calculate the work done at the winding drum, and the work done is given here in the bracket. What I encourage you to do is to stop the presentation and initially try and sketch out the problem that question 7 outlines, and then start extracting the appropriate information from the question. I will show an appropriate sketch on the following slide. So question 7, here's the solution. Extracting information from the question, the truck mass, capital M, is 500 kilograms. The winding drum mass, labelled M suffix D here, is 250 kilograms. The drum diameter given in the question, capital D, is 1.2 meters. So the drum radius, R, will be half the diameter, so 0.6 meters. The radius duration, symbol K, is given as 470 millimeters in the question, shown here. And as always, we convert that into meters straight away, so 0.47 meters. The angle of the incline to the horizontal, angle theta, is 5 degrees, shown here. And the initial linear speed, u, at the bottom of the incline will be 0 because the truck starts from rest. And the final linear speed, v, shown here, is 2.4 meters per second. That's at the top of the incline. If we consider the datum at the bottom of the incline here, then the height of the truck from the datum would be 0. So h1 is equal to 0. One of the first calculations we need to undertake now is to find height h2, because we are given in the question the slope of the incline and the length, it's 30 meters, over which the truck moves. Question 7, solution continued. Here we're going to calculate the vertical height travelled by the truck, labelled as h2 in our diagram. So using basic trig here, sine of the angle, that's 5 degrees, is equal to the opposite side, that's labelled as h2 in the question. That's divided by the hypotenuse s, and s is 30 meters. Here's a sketch of the right angled triangle we're using here. And rearranging for height h2, that's simply distance s multiplied by the sine of the angle, sine of 5 degrees in this case. Inserting the values, height h2 is 2.6147 meters. So now we have the height h2 of the truck when it's moved 30 meters up the incline. Question 7, solution continued. Let's now apply the principle of conservation of energy to this problem. Again, consider the initial energy and the work into the system, and then the final energy and any work out of the system. So at position 1 here, when the truck is at the bottom of the incline and stationary, we will have no kinetic energy because it's not moving. And as the datum is at the bottom of the incline, we'll have no potential energy either. So we'll have no energies at the bottom of the incline. But we do know that the truck is accelerated up the incline. So therefore there must be some forces applied to the truck to make it accelerate up the incline. On the left-hand side of the equation, we have no initial energies, no potential, no kinetic energy, but we do have some work in the system. There must be some work going into the system that will cause the motion up the incline. Considering position 2, now when the truck is at the top of the incline, now it will have potential energy relative to the datum. It's some height h2 above the datum, so we'll have potential energy. We know that the truck has a linear velocity at the top of the incline because we're given that in the question. So we'll have the kinetic energy of linear motion. And because the truck has been pulled up by the cable of the winding drum must have some angular velocity. So we must have kinetic energy of angular motion. We're told to ignore friction effects in the question, so there's no work out of the system. So in this case, the work into the system is transferred into potential energy, linear kinetic energy, angular kinetic energy. If we now consider the information we know that we don't know, well, we don't know the work on the left-hand side because we're actually asked to find that in the question. We do know the mass of the truck, so we've got the capital M in our equation. We always know gravitational acceleration. And we've calculated the h2, height 2, shown here on the previous slide, using basic trigonometry. We're given in the question the linear velocity at the top of the incline, labelled v here. And from our relationship we've used previously of v is equal to omega r, we'll be able to find the angular velocity at the top of the incline, the final angular velocity, omega f here. We can also find the moment of inertia because in the question we're given the mass of the winding drum and we're also given the radius of gyration of the winding drum, so we'll be able to find the moment of inertia. So we also have the I. So we now have all the numerical values we need to evaluate the right-hand side of this equation. Question 7, solution continued. So we can now calculate the initial and final angular velocities of the winding drum using omega is equal to v divided by r. So the initial angular speed, omega I, will be 0 because at the bottom of the incline we're told the truck starts from rest. So if the linear speed is 0 at the bottom of the incline, then the angular speed of the winding drum that's pulling up the truck must be 0. And then the final angular speed of the winding drum, omega f, when the truck has been pulled to the top of the incline, will be the maximum linear velocity at the top of the incline, v, divided by the radius of the drum, r. So that's v of 2.4 meters per second divided by an r of 0.6 meters. So 4 radians per second is the angular velocity of the drum when the truck has been pulled to the top of the incline. We can calculate the moment of inertia of the drum, symbol I here. I is equal to mk squared, so that's mass of the drum multiplied by the radius duration squared for the drum. So 250 kilograms multiplied by 0.47 squared, so 55.225 kilogram meter squared is the moment of inertia for the winding drum. Now we can apply our principle of conservation of energy as outlined on the previous slide. We know that the only term on the left-hand side of the equation is the work into the system. In this particular case, there's no energies at the bottom of the incline for the truck because it's stationary and it's on the datum that we chose to use. And on the right-hand side, we have our potential energy because the truck is now height h2 above the datum. We have the linear kinetic energy because the truck has a linear velocity. And there's also an angular kinetic energy associated with the winding drum. Inserting the values, the truck has a mass of 500 kilograms, g is 9.81 meters per second squared. We've calculated height h2 on the previous slide from trig. That's the first term considered. Second term is a linear kinetic energy. Again, we got the truck mass is 500 and the linear speed at the top of the incline is 2.4 meters per second. And finally, we have the angular kinetic energy of the drum. So that's a half multiplied by the I, 55.225 kilogram meter squared, multiplied by the final angular speed of the drum, which was 4 radians per second, that's squared. So evaluating the work done is 14,707 joules, or 14.7 kilojoules. Here's question 7, solution continued, but the following calculations are provided for reference only. Essentially, we've extended the original question, and we're going to calculate 2 further parameters that are sometimes required to be determined. The first of these is to calculate the drum input torque, labelled T on our diagram. We know that work done, W, that's work input to the system here, is the applied torque at the winding drum multiplied by the angular displacement. In other words, the angle turns through by the winding drum, labelled theta. So from radian measure, we know that linear length S is equal to R multiplied by angle theta, where S in this case is the linear distance travelled by the truck up the incline, R is the radius of the winding drum, and theta of course is the angle turn through. So rearranging the equation for theta, that's simply S divided by R. Inserting the values, the distance travelled by the truck up the incline is 30 meters. The radius of the winding drum is 0.6 meters. So that evaluates to an angle turn through of 50 radians. Just note for reference, I've also calculated that in terms of revolutions, but it is the value in radians we'll be using in the calculations. So from the above work equation, we can transpose that now for torque, T, and that's simply the work done divided by angle theta. We calculated the work done on the previous slide, angle theta calculated above. So that evaluates to an applied torque required of approximately 294 Newton meters. Question 7, solution continued. Again, here's some extra calculations, extending the solution slightly further, but they're for reference only and not part of the original question. I've just repeated the torque here we calculated on the previous slide for convenience. So next we're going to calculate the cable force F. That's this force here in the cable attached between the truck and the winding drum and used to hold the truck up the incline. And we know from previous work that torque, T, is equal to the force multiplied by the radius of the winding drum. So rearranging for force F, that's simply the torque divided by the radius of the winding drum. Inserting the values for torque and for the radius. The force evaluates to be approximately 490 newtons. And sometimes in these questions, we're asked to calculate power. Sometimes it's the maximum power, which would be the torque multiplied by the maximum angular velocity. And sometimes it's the average power, or the mean power. And that's what we're asked to calculate here. I've labelled that as P mean for mean average. So P mean is equal to the torque multiplied by the average or the mean angular velocity. To calculate the mean angular velocity, it's simply the final angular velocity of the winding drum added to the initial angular velocity of the winding drum, or divided by 2, or averaging those two velocities. Inserting the angular velocities, the final angular velocity was 4 radians per second. The initial angular velocity of the drum was 0 because, of course, the truck was stationary. So by default, the winding drum was stationary. So when we average the angular velocities, the mean angular velocity is 2 radians per second. So therefore, the average power, or the mean power, is simply the torque multiplied by the average angular velocity. That evaluates to approximately 0.588 kilowatts. So as I said, they're just additional calculations to question 7, just to show you how the solution can be developed still further. Here's the bibliography used to help generate this presentation, and I hope this has been of interest to you, and thank you for viewing.